Hey to my differential equations class. So this week we're going to talk about numerical methods. So sometimes you have a differential equation that just can't be solved. It's not possible to solve it, but we can still find an approximation of it. And so we're going to talk about three different methods: the Euler's method, the improved Euler's method, and then the Runge-Kutta 4. So the Euler's method takes something that we've already learned, linear approximation, and uses that linear approximation to get an approximation of the function. It is not that great, but it gets you a starting point. So then we come up to the improved Euler's, and we use our Euler's, we use our linear approximation to make a predicted value, and then we improve it. Right, that one's better, but it could still be better. And so then several years ago, there's a group of people came together and created what's called the Runge-Kutta 4, which basically is, instead of just improving it once, you actually improve it 4 times. So this, I'm going to break this up into 2 videos. The first video will give you kind of an idea of what's going on, and then the second video I'll show you an example of how to do those. Okay, let's talk about our 3 numerical methods. The first one is Euler's method. Okay, so let's pretend that we have some function, and even though I'm going to draw it, we don't know what it looks like. But what we do have is we have how it grows, its derivative, and we do have some initial point. Let's call that here. So our linear approximation, what it does is it finds, the tangent line here, and then we know that for values that are close to this tangent line, it's going to be close to our function value. And so we take this and we go just a little ways away and we say, hey, look, this now is a close approximation to what our actual function is. And so then we can call that x sub 1. That's our next point. And so then we can reevaluate our function we can reevaluate what the slope is at that point using our derivative, and then we can say, okay, well, what's the tangent line at that point look like? And so the tangent line at that point may look like that. And so if we go a little bit along here, then we can say that this point right here is pretty close to what our actual function value is. And so if we keep doing that, finding the new tangent line, going a little bit along that tangent line, and then claiming our new y value is an approximation of what our function value actually is, then we can get an approximate idea of what our function looks like. Notice that it's not a great approximation, but it does follow along with what the function is doing. And so that was Euler's method. How can we make this method better? How can we make this method better? Pick a smaller chunk there. And so that smaller chunk that we're moving is called our step. And so if step is normally represented by h, we could pick a smaller h. Okay, so that's the first method. It gives us an approximation. It's not going to be that great. Let's talk about the second method, which is called the improved Euler. The improved Euler, again, you know, we have some function. We're not sure what this blue function is, but I do have a derivative and initial point. If we say that initial point is here, then my y value is up there. And again, what we're going to do is we're going to make a prediction using our linear approximation, using the Euler's method. And so we make this prediction, say, oh, you know, I look like it's going to be there. But instead of using that, we are going to then find the slope at this point also, and we're going to average the two slopes together. So if the next slope is quite a bit higher, then it takes this low slope here and kind of raises it up a little bit. And so then we average these two slopes together, and so it will pull this point up just a little bit, and so it's a little bit closer to the actual value. And then we do that again. We find an original slope, we go to the end, we find that slope, we average the two slopes together, and then, you know, so if my second slope is higher, then it will pull that original one up. If my second slope is lower, then it'll bring it down a little bit. And so because it averages the two slopes together, you actually get closer to your actual function value. So now, what about the Runge-Kutta 4? The Runge-Kutta 4, it's called an order of 4 because now when we go and we make our step, now we're going to break that up into 4 different sub-steps, and we're going to find the slopes at each one. And we're going to make a weighted average of those 4 slopes. So this breaks the step into 4 sub-steps and finds the weighted average of the 4 slopes. So it's called a Runge-Kutta of order 4 because we did break it up into 4 sub-steps. And the nice part about breaking it up into the 4 sub-steps is that it reduces the error to 2 to the negative 4th power. And so we get something that's very, very accurate for relatively few calculations. This is more involved, but it does give a very accurate representation of what the function would be for relatively few calculations. So hope those make sense. In the next video, we'll be playing around with Excel to see how those actually work.